Thank you very much, Virginia. Thanks for this very kind introduction. Also, thank you, Kimberly, for inviting me here. My talk is entitled EURAMED's Vision on Medical Radiation Protection Research, because that's what EURAMED is for. And as you read from the title, I will look a little bit more into the vision and try to give you small examples on that. So, first of all, what is EURAMED? I will try to explain that with the vision and the mission statement that we conducted last year, actually, and also presented it at the European Radiation Protection Week in Oxford, when we had our kind of official starting. Also, the legal entity we are just right now since 1 week ago, and therefore I'm no longer the president, but the past president who is now speaking to you of EURAMED, because since yesterday we have a new board. So our vision as EURAMED is to lead European research activities in medical radiation protection and harmonizing clinical practice to advance the European radiation protection safety culture in medicine. And this vision really leads to 4 dedicated mission statements that we did at the very beginning. So what we want to do with EURAMED is to improve the medical care through sustainable research efforts in medical radiation protection, identify common research areas in this field, and serve as a platform for medical radiation protection research. With that, we want to develop aligned approaches and responses to European research call, and obviously we would like to collaborate with institutions like the ICRP Committee 3 working group. So why do we want to do that? I mean, this is a pretty old UNSCEAR document meanwhile, but what is in there is still true, right? The committee concluded that medical applications are the largest man-made source of radiation exposure for the world population. This is obviously especially true in countries of the European continent. The committee also concluded the population exposures from the diagnostic and therapeutic uses of ionizing radiation were likely to be increasing worldwide, and this is particularly in countries where medical services are in the earlier stage of development. However, further and more comprehensive analysis would be required in order to refine global estimates and establish important trends, and we are still at that stage. Also, this document is 17 years old. The analysis of radiation risk from diagnostic medical exposures required detailed knowledge of organ doses and the age and sex of patients. And because we are a European association, we looked for what is the distribution of those values due to different applications in the various European countries. And when I read this report in detail, I was pretty happy that no longer Germany is leading this kind of graph. So I'm a bit sorry for our Belgian friends who are now in the pole position here, where we have a per capita effective dose of nearly 2 millisievert per year, and you see that the very, very main component of this is due to computed tomography. It had also been mentioned that interventional radiology is a major contributor as well. Also, the number of applications is much lower. So basically, this already shows you where we will have to focus. Additional numbers that we might have to look for is that all over Europe, a total of about 5% of the doses go to the counter of nuclear medicine. I know that in the States, for example, this is quite a different number. So what is the specifics which we have to take in mind when we are talking about how to optimize, how to do research for radiation protection in medicine? Well, there is one very specific that we have when we talk about medical radiation protection. medical radiation protection should always be related to situations where we are really in the planned situation. So we really can look for all the aspects like justification and optimization. However, the limitation is not given in that sense for the medical field. However, we want to try to limit the dose as much as possible, but without stating, without doing that completely or having a complete limit. This could not be the case because we have to have the benefit on the first position here. So if you remind what I told you very much at the beginning, we are looking for harmonization as one of the aspects of optimization and limitation. This is a graphical show of the differences, in this case of entrance surface doses, because that could be measured easily, to patients per examination in different countries. And it's even older graph than the report that I showed you before, but it's still in similar domains, as you can see. But this is a very nice graph, therefore I keep it in my presentation. And here you see that the entrance surface doses for two different investigations are really varying, and please look at that, the x-axis is on a logarithmic scale. So they are really varying about orders of magnitude. So obviously, it is a big, big need to harmonize the practices. Okay, let's take a look on why this is important and also why this is important in imaging. So if we look for patient exposure in digital radiography, we have various numbers that we can always use. A virtual colonoscopy results in doses like 36 to 50 millisievert. But there is an issue of considerable concern, and that is the excessive use of fluoroscopy in interventional procedures today. And if you have a high-level fluoroscopy mode, then you get a very high contrast resolution, and that might be good. But that means that patient entrance surface dose rates can be approaching like values like 1 gray per minute. And to compare that also, I know that this is an unfair comparison because it's not obviously a planned situation. For the Hiroshima survivors, we had investigations for regions between 5 and 200 millisievert. So one thing that we would like to do is really to look for the distribution of doses in organs, and we see this might be important because there are obviously, as has been shown in this graph by Helmut Schlattel, there are many, many decades of differences in the doses to various regions of an organ. Here for a cardiovascular intervention, you can have a dose distribution within the lung by a factor of 100 or even more. And then, this has also been mentioned by Colin, if you do interventions, you obviously have also a problem to protect those people that do the interventions. So it is better to keep the time as short as possible, to keep the distance as large as possible, and also to protect yourself as good as possible. And then, which we evaluated together, and many groups do that together with Bill Orison, for example, you really need to measure the dose in a reliable, easy, and fast way, and you should have a possible warning in these cases. So, in general, we have a definition of diagnostic performance, and that gives us the optimization proposal that we have, and it starts from the image generation to the detection to the presentation, and we really can try to optimize on every single aspect, and that would then allow, if we couple this diagnostic performance, and it's all about diagnostic performance in diagnostic imaging and not about image quality, that would then allow us to really optimize in terms of dose. So let's have a very brief look in nuclear medicine. Also there we need optimization, and I gave a talk about the specifics of internal dosimetry this morning. Here we have a planned situation to an internal exposure, and also this gives us the way with different types of models to get to a better dose distribution or estimate of the dose distribution, but also to help us to calculate the, for example, S values if we have correct phantom distribution that we need there. So I would like to be brief here. We have to be very careful in this case about uncertainties because we are really talking about individual patients and those that suffer from diseases. That's why we are investigating them. And now I'm lost in time, obviously. And when the diagnostics, for example, or the therapy will change, then that means that we have a specific organ that is influenced by the illness, and that might change completely our biokinetic models. In therapy, we are also looking about ways to optimize, and this would be something that research will have to focus on, for example, with ion therapy or proton therapy, and the question, what can we achieve with that? Here you see a graph of a plan of the volume for a tumor, where you put the therapeutic dose in this tumor volume, and how then the different kinds of proton beams, or in this case carbon beams, will add on to a dose distribution, and compare this with a photon distribution. To make this more practical, after I've shown you the picture of the Heidelberg Ion Therapy Center, you can see that, for example, in these two plans for the different procedures here, photon therapy on the right side and ion therapy on the left side, and you obviously see the difference in how to spare the rest of the regions, the healthy tissue, which could be helpful. But we have to determine how we optimize the procedures, how we optimize the approaches, how we minimize the side effect for an individual patient. It might be that for a specific individual patient, this optimization doesn't make much sense, and Catherine West this morning showed what that means. For some patients, there might be a larger benefit from doing such optimization with proton beams, for example, than for others. That means, in general, in therapy, we need to optimize on an individual basis the TCP to NTCP ratio, and we have to check what is acceptable in terms of costs and so on. And then we have to talk about how can we compare these procedures in a clinical environment. We need to know for which patient which method is most suitable and which is necessary. So I try to summarize after these effects, and our new president stated from EURAMED, improving people's lives through innovative multidisciplinary research in medical radiation protection, from a basic statement from Jonathan McNulty from one of the groups. And we are really trying to work on this, and this is what we want to be measured, let's say, after a decade of further work that we are about to do. So what are the principles of optimization, where we can go this? Obviously, we have to talk about justification. We have, in the clinical environment, determine the risk, determine the benefit, and to communicate that. And then we have to work on harmonization of practices, especially in the context of individual radiosusceptibility and radiosensitivity. And we have to deal with the question, how do we individualize procedures in terms of exposure, image quality, and outcome in a standardized way, depend on patient status. We have to optimize the occupational exposure, and we have to work with educated staff and scientists. And especially with the education of scientists, that's something that EURAMED will also focus on. You can read all this in the strategic research agenda that we were happy to provide and discuss last year, and that was published in Insights into Imaging by the 15th of February of this year. And I'd like to finish with a short outlook. It would be of great interest for optimizing medical radiation applications in terms of radiation protection, and that's what we are here about, on a per-patient basis, to investigate how individual patient sensitivity, even on an organ level, could be identified fast from investigations done basically just for diagnostic purposes, or how to develop specific characterizing procedures that allow fast optimization. And it's important that this is done in the clinical practice, and you see this is a very close link to the other platforms as well. In terms of dosimetry, it would be of interest also to develop fast applicable methods for dose determination, as well as for patients, and we should not forget about that because that's sometimes done, as for staff, and also for local dose determination for the modern technologies like proton ion-on mutant therapy. With that, I'd like to thank you. You can read the rest of the text yourself. Thanks for your attention, and I think we'll have time for questions later on. Thank you very much.